Hello everyone, and welcome to this week's PTC Nordic Talks webinar, where we are excited by having Samuel Scheidegger from Aixia from a session on artificial intelligence in production, enabling traceability and quality control for smart manufacturing. But first, a very quick introduction by myself for those who haven't been here before. So my name is Torbjörn Peterson, and I'm the Alliance Manager for PTC in the Nordics, and we are running these webinars same time every week, where we invite customers and partners for some inspiration on digital transformation to see what is possible and how to make things happen. And all the past webinars have also been recorded and are to be found on the registration site. And the agenda for today is first a very quick overview of PTC by my colleague Carl from the customer success team, and then Samuel will start by introducing himself and touch base on a few challenges, how to address these, and then explain how some of the business outcomes. And at the end, we are also having a Q&A session, so please keep your questions to the end. So over to you, Carl.
Yep, thank you. Yep, thank you for the slides. So PTC is an international software company with headquarters based in Boston. We are developing software mainly for manufacturing companies since 1985. We offer tools for the digital transformation, such as CAD for design, PLM for managing data, IoT for connecting products or manufacturing operations, and augmented reality to visualize and interact with the digital thread. So that's it. To you, Samuel.
Great, thank you. First of all, thank you for having me. It's really exciting to be here, and I guess we get started. So yeah, welcome to my presentation on using AI in production, enabling traceability and quality control for smart manufacturing. And this work has been conducted by my colleagues Jinan and Victor and myself. So my name is Samuel Scheidegger. I'm the co-founder of Aixia, and I'm also the co-founder and CEO of Asymptotic AI, which is part owner of Aixia. My background is within signal processing, machine learning, and IT infrastructure, and I've been working with deep learning infrastructure since 2016. And at that point, we were the first in Europe to deploy NVIDIA's AI compute service, DGX, and our work later became the world's first full-stack AI-ready infrastructure, AIRE. And I've mainly been working within the automotive industry and smart manufacturing. So the agenda of today has 4 steps. First, I will briefly introduce Aixia and AI as a service. Secondly, I will present a project that we have been working on together with an engine part manufacturer in Trollhättan called Sancera. And then I will show a demo of what we have done so far. And finally, I will talk about what the next steps are. So at Aixia, we're providing tools, software, and services within AI and machine learning. And our vision is to create the best AI experience for our customers. So before we jump into what we do, let's define what is an AI experience. So an AI experience to us is a data-driven workflow that consists of 3 main components. We have data. The customer usually has some kind of data in place, but we also introduce new data sources to enable better data-driven decisions by adding, for example, new sensors. An AI system that we deploy and integrate to our customers' production pipeline to help them make better business decisions. And we use the business KPIs as the most important feedback to refine the systems to maximize the actual business value. So we think that the best way to create the best AI experience is to provide AI as a service, where we take a complete responsibility for everything from the data center, the AI development, to deploying AI algorithms in production. So by offering AI as a service, we lower the barrier and cost for our customers to use AI in their business. So we provide access to state-of-the-art AI models, GPU servers, or edge hosting, and we can reduce the lead time. We have a short time to market, and we can provide instant business value, and we have a clear scale-up plan. And we achieve this by using our 2 services, IQ and Snap Access. We have IQ, which is a scheduling platform to efficiently utilize GPU compute servers, for example, for training deep neural networks. And then we have Snap Access, which is our data lake solution to collect, organize, and annotate data, for example, to create data sets to train neural networks. To deliver AI as a service, we use our internal tools, IQ and Snap Access, to orchestrate the pipeline. So the AI as a service pipeline has 5 steps. So data inventory, so we help the customers to look into their internal data, evaluate what is important, and if they should collect any additional data. And then we go to the customers, install new sensors, set up interfaces to our data backend, Snap Access Core, and then we build up machine learning ready data sets by annotating the data using our semi-automated tools. And here, if the customer currently has a manual process, we integrate to that and leverage that to generate labels. Then, using the machine learning ready data sets, we adapt and train our AI models to the customer-specific use case using our deep learning services, Snap Access and IQ. Then, finally, the most important step, to deploy and integrate the AI models to the customer's production pipeline. So here is a quick overview of our pipeline that we use to deploy AI models at Sancera's production plant. So we start up to the left with data collection. Here we can either integrate towards the customer's existing systems, or, as in Sancera's case, install new sensors like cameras. After that, the data goes through our data processing pipeline, where we do data selection, data labeling, data validation, and then finally, data preparation to create machine learning data sets. And these data sets are then used to train and evaluate state-of-the-art AI models. And the trained models are then optimized and validated before they are deployed to our production AI servers to start making automated decisions. So now let's take a look at our project together with Sancera to see how our pipeline is used in production. So in this project, we are introducing automated quality control and traceability into their production line by using a camera-based AI system. Currently, we have 3 cameras deployed, which you can see in the image to the right. So far, we have been working on adding traceability and quality control to Sancera's production line. The value we are providing by adding traceability is to enable value stream mapping and optimization, monitoring and searchability, and predictive maintenance of machines and tools. And the goal for automating the quality control is to reduce the waste and the production cost by enabling early detection of faulty parts to improve the sustainability, the speed, and the scalability. So here is a close-up view of the 3 cameras that we have deployed in the production line. So all cameras take a picture of a different text marking on a connecting rod. So here are example images from the cameras. First, in the upper right corner, we have the date code, part number, and the serial number, which together is a unique identifier for each part. So we can use these numbers to track one specific connecting rod through the entire production line. And then at the bottom, we have the steel batch code and the die number, which tells us which steel and which die was used for casting the part. And each part is also connected to a specific certificate, which contains more information about the casting, like mechanical and chemical measurements and their specifications. And by combining the steel batch code and the die number, we can associate each connecting rod to one specific certificate. And in this project, we want to automatically identify and decode this number using an AI system. And then we can use the serial number to track each specific part, and we can use the batch code and the die number to enable certificate search. And this enables traceability of all products in the manufacturing line. So in order to achieve this automatically, we built a system with the following process. So first, the images are collected from the production line. Then the images are analyzed using an AI system to read the serial number and the batch code from the connecting rods. And then Sancera supplier provides certificates for the steel and the casting process that was used to produce the parts. So we extract information from these PDFs to make them searchable. And finally, where it all comes together, a system where we can browse and search and find information about, for a specific part. So here is a topological overview of the system. Out to the right, we have the cameras that are connected to the robot in the production line. and the cameras are triggered by the robot to take images, which are then uploaded to our processing cloud, where they are analyzed and ingested to our data backend, SnapAccess. And the steel certificate, they arrive in the form of PDFs, and the information from the PDFs is extracted and also ingested into SnapAccess. So here I want to highlight the development of the AI models for the process. So first, we collect a set of images from the cameras in the production line. Then we label the images by marking each individual character to create a machine learning ready data set. And these data sets are then used to train AI models on powerful GPU servers to automatically read the characters on the connecting rods. So after training and evaluation, the AI models are ready to be deployed in production. So when the AI models are deployed, they can be used to automatically read the serial number directly from the connecting rod. And this is where we enable tracking and searchability of specific parts using the unique identifier from the serial number and the date code. So by having this unique identifier, we can also associate metadata such as quality measurements to each individual part. So similar processes are applied to train AI models to read the steel batch code and the die number. And we store these values connected to the unique identifier so that we can associate each individual part to a specific certificate. So the certificates, they come in different formats and are typically not structured in a machine readable way. So we need to standardize the format and make it machine readable in order to make the content of the certificate searchable. So we do this by using optical character recognition algorithms and other text processing methods to convert the certificate to JSON, which is a machine readable standard format. And here in the example, we can see that information like the mechanical and chemical data in the PDF is converted to machine readable JSON format. So now I will show you a demo of the system in production. So the scenario is that during the sampling process, I want to look up some information from the steel certificate for a specific connecting rod. So first, I will search for the connecting rod in the system with a unique ID. Then I will inspect the images of the connecting rod. And after that, I will search for the content of the certificate of this part. And then finally, I will retrieve the steel certificate in PDF formats. So here is the interface of the system. So if I want to find my specific part, then I first go to search part here. Then it brings up an interface where I can enter the serial number and the date code and the part number of the part that I'm interested in. So here, for example, I want to look up for information of a part with serial number 1723 with the date code 22W105, which then has this part number. So then when I hit search, the system will bring up the information that is associated with this specific part. So first here, we have the station time, which is a timestamp for when this specific part was at a specific station. Then we have the date code and the serial number and the part number that I entered for the search. And then again, we have the die number, which is the identifier for the specific die that was used. And then we have the steel batch code, which is an identifier for which steel was used for casting the parts. Then under this, we have the images that are taken of the part. So if I start by clicking the serial image here, then we can see the image that was taken that contains the information that we're interested in. So here we can see that the system has extracted the serial number, the part number, and the date code, and inserted it to the system. Then if we go back and look at the batch die number, then we have, in this case, we have 72 here, and this was then extracted to the system and stored. And the same for the steel batch code, which in this case was C. So then the system, when it knows the steel batch code and the die number, it can associate this specific part to one specific certificate based on these two values. And then the system will provide me with a link to this specific certificate. So when I click it, it will bring up all the information from the certificate. So here we have information like the batch number. We have article numbers for in different forms, like the Sancera's internal part number, Volvo's part number, and so. And then we also have results from some tests that were made when creating the part, and then we can see that the results from the test were okay, and then we have some remarks that were done when making the tests. Under here we have the chemical data that was extracted from the certificate, and also the mechanical data. Then here I can download this information in JSON format in case I want to do any further processing or insert this information to another database, or I can download the original PDF from which the information was extracted. So here is the PDF from which this information was extracted. So that concludes the demo of what I wanted to show you. So to summarize, currently we have 3 cameras deployed in the production line. We have online AI models up and running, and the outputs are continuously inserted to the database. And as a next step, we are writing a paper on the machine learning lifecycle together with the Stena Industry Innovation Lab. And then in addition, we will add cameras to more stations to increase the tracking coverage. And we will also start collecting quality measurements to enable quality control and predictive maintenance. So that concludes my presentation. And first of all, thank you for listening. And if you're interested in our technology and services or need help with digitalization, reach out via email or add me on LinkedIn, and I will copy paste my email address and LinkedIn address and so in the chat, so you have easy access to them. Yeah, and I think we have some time for questions, right?
Thanks a lot, Samuel, for sharing all the fantastic AI use cases here. And I'm sure we have a lot of funny questions from the audience. So please go ahead, raise your hand and ask the questions you might have. I open up for you now. You could just speak up. I think we had one here. I'm just opening up. Yeah, welcome. Please go ahead.
Hello, Samuel. It's Graham Cox here. Can you hear me?
Yes, I can hear you.
Samuel, thank you very much for this excellent presentation. It's really great to see this application of AI into manufacturing operations. Sometimes in this domain, we've encountered challenges of latency and responsiveness of the AI capability because of the speed and timing required in the manufacturing operations. Have you encountered this problem, and how would you address this?
Yeah, well, we have encountered this, and we have thought about it. Like in this case, we get approximately 3 images per minute, which then is not a problem. So then we run these like the computations in our cloud or in our data center. However, when we encounter as you say, processes that are much faster, then we will deploy edge compute services. And we come from IT infrastructure background, so we have the knowledge and experience of building GPU servers, and we will then build that to the best of our ability to make the processing as fast as possible. And then, of course, also we can work with optimizing the models and trying to find the best trade-off between the accuracy and the computational aspects. Sorry, I couldn't hear you.
Thank you for your answer.
Yes.
Great, thanks. So we had another question from Peter Jensen as well. Would you like him to ask you a question directly?
Yeah, sure. Yeah, so thank you again for the presentation. I also think it was interesting. What comes to my mind is, so how general or how custom built is this approach? Because generally using OCR algorithms can be tricky on this kind of somehow it's laser engraved maybe or something like this. So can you give a bit of words on this? If we would be utilizing the same solution in our production system in Danfoss, do you expect that it should be retrained and a lot of custom, or is it directly transferable?
Yeah, in this case, we had to build our own data sets with the specific font that was used to engrave these parts, and like the algorithms themselves are transferable to other problems, but they are adapted to like customer specific requirements or customer specific use cases with special data sets when required. However, we try to automate this like labeling, like the labeling process is quite costly. So in this case, for example, we put a camera right after the engraving so that we know which number was actually printed on the part. So in that case, we could do like a simple localization of the characters, but then we know what is supposed to be printed on the part. So in that way, we managed to produce quite big data set very cheaply. But that's something we work like I think I mentioned that in that, like we work a lot with like trying to automate the annotations to as a big degree as possible, because this is like one of the absolute biggest bottlenecks in this type of things.
Okay, great. Thanks for elaborating.
Thanks. We have another question also from Vesa. Would you like to ask your question, Vesa?
Yeah, okay, thank you. I was interested about your MLOps process, the operative process, and could you describe it a little bit closely?
Yeah, well, it's based on like microservices, and we use like standard tools to deploy the models to GPU servers, and we use standard tools for like monitoring like both the processes, but also the like algorithms themselves. Like we try to monitor the performance of the algorithms and try to detect either if there is like in the production plants we have like robots moving around, and sometimes heavy things are dropped on the cameras, and then it might be damaged or get out of focus or something like that. So we try to monitor these things, for example, as well, like both the input data and the output data from the like machine learning specific things. Did you have anything more specific in mind?
Yeah, that's interesting, because MLOps hasn't been used too broadly, and you showed process out of that, and how can you use the knowledge for MLOps and use it again?
So sorry, you broke up there in the last sentence.
Yeah, can you store it to like a warehouse? Those that knowledge about as you described certain type of grip is not can't be used, and you store it and you can't use it again. Doesn't do the same mistake again.
Yeah, we're working
use case storage.
Yeah, we try, like, of course we try to learn from all the projects that we do, and we try to build everything like as standardized as possible, so that we can reuse as much as possible. Like we both have models for specific use cases, and then we have like annotation process, like the data backend is built to handle many different types of data, and so we try to make everything reusable to as a big degree as possible. But of course, we always encounter new problems, so we have to find new solutions for things. But our goal is to be able to like get up and running as fast as possible with a new customer.
Okay, but you have a standardized process for doing that.
Yes, yeah, absolutely. I can show you. I think, let's see this slide.
Yeah, that one.
Basically describes like the different steps that we go through, and here we reuse as much as we can in every step.
Okay, thank you.
Thank you for the question, Vesa. We have another question also from Shriram, and would you like me to ask you a question directly to Samuel? Shriram?
Yeah, hi. Can you hear me?
Yeah, we can hear you.
Yeah.
Hi, Samuel. So I just wanted to understand how much time I took for the model development and fine-tuning for workable accuracy.
In this case, it was mostly a question of the amount of training data. For the serial number, for example, I think we ended up at approximately 20,000 images labeled. But as I described before, like this process was automated to a high degree, so it was not like much labor. It was more a question of waiting for the parts to go through the process. And then we had OCR techniques ready to be deployed, but then we made some adaptations for this specific use case, since we knew some of the patterns, like how long the serial number should be, for example. So we utilized this information to get like increased accuracy further. But like from having the data labeled and ready to go in like a machine learning ready data set, the process of developing a new model is not that long. It's certainly below 1 month.
Sure, thank you, Samuel. Just one more question. So if it is a very high speed line, will your camera and the model output and everything, will it have an impact, or will there be a delay time? How does a high speed line, I mean, how can you extend this to a high speed line?
So the cameras, in this case, we're using like network connected cameras, which is the limitation on the the number of images per second. Here we end up at around 15 with this resolution, like 15 images per second with this resolution. But then if we have like higher requirements, we can go to other interfaces to get higher camera specific interfaces, which then have a higher cost, of course. But like there is hardware available to get to higher speeds. And then on the processing time that we spoke about before, like then there is like we have the latency aspect, and then we have the bandwidth aspect, and like the bandwidth we can always solve by adding more compute, and then the latency, then that's a question of having like a small model that is able to produce the results as quickly as possible.
Sure, yeah, thank you.
We have time for one last question, so anyone who would like me to raise your hand or speak out. I have one quick question otherwise. Based on your experience, who should get involved in these kind of projects? You think, from an organizational point of view, what would be the good stakeholders to make sure that they are engaged here?
I think I really talk to like the technicians or like process operators that really know the process that they are working with. Like they know the what is the difficult part, and they know like often they have an idea of how it could be solved. And it's really important that we work like we are not the experts on their processing line. They have to be the experts on that, but we can be the experts on the AI system and those things. And so for us to like really be successful, I think that's the optimal combination, or the optimal people to talk to.
Yeah, all right, thanks. Friends, time is unfortunately running out, so many thanks everyone for joining, and a special thanks, of course, to you, Samuel, for sharing a lot of great stuff here. And also, please stay tuned for the next Nordic Talks already next week on how the winner of the Swedish CIO 2030 Sustainability Project make use of IoT in beehives. That's going to be quite interesting as well. So with that, I wish all of you a fantastic weekend, and maybe, if you have some time extra, Samuel, you could stay on the chat, and maybe you have time to answer some questions here. So many thanks and have a great weekend.